Welcome everyone. My name is Advait Datar and I will talk today about flocking algorithms to address the source seeking problem and some experiments with quadrotors. This work is done in collaboration with Peter Paulsen and Professor Herbert Werner at the Technical University of Hamburg. Before we jump into the details, we'll first motivate the source seeking problem by considering two scenarios. On the left, you see the radioactivity level contour plot after the Fukushima disaster. And on the right, you see an oil spill scenario. One can imagine that in these scenarios, we can deploy a fleet of quadrotors or say underwater robots that could locate regions with highest concentrations of radioactivity or that of oil concentration. With such scenarios in mind, we can now define the source seeking problem in an abstract setting. We consider a group of N agents, which could be underwater robots or quadrotors, that are deployed in some region of interest. Each agent is equipped with a position measurement sensor, a communication device, a concentration measurement sensor, and some computation capabilities that allow it to complete the source seeking task. The problem can then be defined as to design distributed control algorithms that cause the group of agents to flock towards the source. So we treat the source seeking problem as a minimization problem. Note, however, that the practical problem involves finding the region with the highest strength of the field, such as radioactivity, but we can invert the sign on the cost to write it as a minimization problem. Now, momentum methods have been around in the optimization literature and are known to speed up convergence rates and dampen oscillations. These methods are all the more interesting to us because our mobile robots naturally have momentum and inertia to them, and the dynamics of these methods can be easily augmented with the flocking dynamics. We would like to note here that the analysis that we will pursue later will be in the continuous time setting instead of a discrete time setting, and that's because we want to prove asymptotic properties which are slightly easier to be shown in the continuous time, and we want to avoid a sort of tangential discussion on step size selection and so on. Now let's make things concrete by considering the Newton method with momentum. We have an f which is strongly convex and twice differentiable, whose minimizer we seek. The standard Newton iteration is given by the expression in 1, where nabla squared f is the Hessian and nabla f is the gradient evaluated at instances xk. Now we can write an analogous continuous time version of these dynamics as shown in 2, where we can see that if we now Euler discretize the dynamics in 2 with a step size of alpha, we obtain the dynamics in 1. Now the trick here in momentum methods is to add momentum to these first order dynamics. This is done by adding an mx double dot term to these dynamics to obtain the equation as in 3. We can rewrite the second order differential equation in 3 as a system of first order differential equations by defining a new variable v, which is defined as x dot. Now we keep this in mind because we would later want to augment our flocking framework by adding this sort of forcing term here. Before we do that, let's make clear what we mean by flocking dynamics. So flocking or flocking dynamics is basically an attempt to explain the emergent behavior that is seen in large groups of animals, such as the flock of birds that you see in the left picture or schools of fish. So there are multiple particle-based models that try to explain this emergent behavior by simple rules followed by each agent. One such model was proposed by Craig Reynolds in 1987, where he postulated that if each agent would follow 3 simple rules, which he called cohesion, separation, and alignment, it would lead to an emergent behavior of the group. These 3 rules basically mean that each agent tries to stay close to its neighbors, tries to avoid collision with its neighbors and tries to align its own velocity with the velocity of its neighbors. When written in precise mathematical form, we obtain flocking dynamics as in 8, where q is the position and p is the velocity. So this term here can be seen as a forcing term because p dot is acceleration. V here denotes the particle-particle interaction field, and one can think of this as a force field. An example of a potential field is that of a gravitational field. However, while simulating planetary motion under gravitation, we will not have these two terms. These two terms here come from the alignment rule, which says that each agent tries to match its own velocity with the velocity of its neighbors. That is this term, where L is the Laplacian matrix. And this term comes mainly due to the damping or some friction involved in these agents. Now, observing these flocking dynamics and recalling what we saw in the momentum-based Newton method in the continuous time setting earlier, we can add a forcing term to these flocking dynamics, such as here, where psi now is the underlying source field, which we assume to be smooth enough to have these gradients and Hessians well-defined and convex. Now, in order to show that this is a good idea, we have the following theorem, which analyzes the dynamics shown here. So the theorem says that if psi is twice differentiable and convex, these dynamics are stable, meaning that the trajectories remain bounded for all times. Moreover, using Lassalle's invariance principle, we can show that the trajectories converge for all initial conditions to the largest invariant set within calligraphic W, which is given here. Let's quickly look at the proof, which follows standard dissipativity based arguments. We can define an energy type function here as shown here, where this term is basically the kinetic energy. This term is the potential energy due to interactions amongst agents, and this term is the potential energy due to the external the external force field. Yeah, now we can differentiate this equation to obtain that E dot is non-positive, meaning that E is non-increasing. This implies that E at any time t is upper bounded by E at time 0 for all times, which implies then the boundedness of trajectories. So this is Lyapunov stability, or stability in the sense of Lyapunov. In order to prove asymptotic stability, we need Lassalle's invariance principle, by which then we can show that all trajectories converge to the largest invariant set contained in W. For a special case of quadratic fields, we have the following corollary. Now, this says that if additionally psi is strictly convex, quadratic, and has a unique minimum located at QS, then the center of mass of the agents, which is basically just the average of all agents, converges asymptotically to this source. In order to discuss experimental results, we should first talk about the plausibility of assumptions that we made for our theoretical analysis. We made 3 assumptions. A1, agents were modeled as double integrators. Assumption 2 was that the scalar field is assumed to be convex and twice differentiable. We also assumed that each agent had access to the gradient and the Hessian evaluated at the agent location. Now, in order to make the first assumption plausible, we first designed a local velocity controller which ran at 100 Hertz in the velocity loop, which is shown here as GWell. We tested the tracking performance of GWell by trying out different p-desired trajectories, where p-desired means the desired velocity trajectories. Because the flocking loop is running slower at 20 Hertz, we observed that the performance of GWell under reasonable p-desired trajectories that could come out of flocking could be approximated by a single integrator, which meant that the model of our quadrotor as a double integrator was reasonable for our setup. The next assumption that we made was that of convexity and differentiability of the fields. Well, we are aware that most of the fields in practice would not be convex, and moreover not even differentiable perhaps. For such situations, we believe one could find smooth approximations or smooth local approximations and use the gradient and Hessians of these approximations in case of non-differentiability. Whereas for non-convexity, one can look at these results as local results instead of global ones. Moreover, we also did some experimental tests with non-convex fields to see the applicability of the algorithms in such scenarios. We, however, like to point out that this is still ongoing work, and we're not yet completely clear on how to treat non-differentiable and non-convex fields. The third assumption that we made was that each agent has access to the gradient and Hessian information. In order to make this assumption plausible, or to test the plausibility of this assumption, we injected random noise centered about zero and with a magnitude of plus minus 5% of that of the field strength to see the errors that we obtained in the Newton and in the steepest descent direction. Well, because the gradient and the Hessians are not available, we solved two small least squares problems on board and got these estimates. We used a heuristic here that whenever the estimated Hessian was not positive definite, we simply used the steepest descent direction. This figure shows shows a histogram of errors in degrees for a sample experiment. We see that for most of the samples, the error lies between plus minus 45 degrees, which says that in spite of this injected noise in the measurement, the agent is able to locate the correct quadrant in which the source lies and thereby move towards it. Now, before we go to the experimental results, let's look at the setup that we have in our lab. The left figure shows a schematic of the indoor positioning system that we have. Each tripod has at the top and at the bottom an anchor which acts so the system together acts like an indoor GPS system. On the right, you see the Crazyflie 2.1 experimental platform. Both these hardware setups being developed and sold by the company BitCraze. Because the software on Crazyflie is open source, we were able to code our peer-to-peer communication protocol so that each Crazyflie could talk to its neighbors. Additionally, because there's no scalar field involved in our experiment, we had a virtual scalar field, and we gave each Crazyflie the value of the field based on its location artificially. Now let's look at the experimental results. So, to conclude, we've proposed a distributed control algorithm that addresses the source-seeking problem. We theoretically analyzed the convergence properties of the proposed algorithm and then presented experimental validation with quadrotor experiments. With that, I thank you for your attention, and I'll be happy to try and answer your questions.